title of my talk is Generic Programming Must Go, which is actually, if you think of it, it's good news for the Go programming language. They don't need to do nothing. So, pretty cool. So, this is a tale of a journey I've taken for the past year plus while I was trying to design a good allocator, which is kind of a silly thing. Sounds like a trivial undertaking. I decided to call it heap building blocks because there are some thread building blocks by Intel which are nice. And there's heap layers which predate heap building blocks. I think heap building blocks are pretty neat. But essentially today they're more of a pretext that illustrates something else. So, let's think about design a bit. Consider like 1960, procedural programming was born, and people wrote code, and that code would run on data that hadn't been seen. The code is known, the data is not known. The code churns to the data, and we're done. So that was procedural programming for you, very straightforward. But then, people want to reuse more, leverage their code better. So two more paradigms were born, which are actually, there are quite a few more similarities than many people give them credit for between these two, object-oriented and functional. They both have at core the notion of working with as of yet unseen code. What would be the means for object orientation? Talk to me. Dynamic dispatch. So this is sort of the core of object orientation. You have polymorphism, you manipulate the base class objects in the same manner, and that code that works with the base class objects is going to essentially leverage code that has not been written yet. Which is pretty neat. I mean, it was a thing. Similarly, functional programming does the same thing. The best abstractions of functional programming involved what?
Higher order functions.
HOFs. Higher order functions and lazy evaluation. That means you write code, again, that works with code that has not been written yet. Map would be sort of the most trivial, or fold, or would be the most trivial incarnations of this idea, which is grand. It's huge. Because you write one line of code, and then it's going to be executed for eternity, especially if it's an infinite loop, right? So, come again? No, in functional programming you can't. You just can't. You gotta actually do something. Okay. And is this the laser? Do I have a laser?
No.
Okay.
Well, it's supposed to have a laser, but it's very faint.
Okay, let me see. Okay. So in generic programming, I kind of sat down and thought a lot about where does it stack in the hierarchy? Because clearly generic programming is kind of nice, it's good, it has results, it does things. STL iterators, all of these things, STD algorithm, there's good evidence that generic programming is great. And my conclusion is that generic programming works with unseen data, obviously, as everybody does. Unseen code, but also in GP you have a new thing. Unseen data layout. It's the shape of the data I haven't seen yet. And that's why generic programming tends to create very efficient designs, because it adapts automatically, automagically if you wish, to the layout of the data it works on. So you have your iterators, and you have an array, and it has a layout that's very linear and nice and contiguous, and you have an algorithm that works on the array, treating it as a pair of iterators or a range, and boom, you go through the array screaming like crazy. But then you can do the same thing with a memory map file, or even a file, or even a structure that's not contiguous, such as a rope. So, so the engineering programming is not really bringing, it also works with code that hasn't been seen yet. Because, you write things and you execute, you do things in different places and different times. So there's leverage. But it's also this notion, I haven't seen the way that your data looks, the way your data sits in memory, the way your data kind of, does things. And this is sort of the new thing that engineering programming brings to the fore. It doesn't sound like much, but it's a hell lot more efficient than the indirect calls of functional programming or object orientation. So far, so good? Make sense? All right. Well, I figured, I figured I don't care for either of these. So I said I tried to care and I failed. So let's see what generic programming is defined. It's a program paradigm whereby, nice word, fundamental requirements on types are abstracted from across concrete examples of algorithms and data structures and formalized as concepts, with generic function implemented in terms of these concepts. What word comes here twice? Concept. Concept is a name for a thing, right? Generic programming is very intensive on nomenclature. It wants to give names to things so it can operate with these, define the names, define their interface, and then let everybody do their layout the way they wanted, and then you have your generic algorithms. And that has worked great. So what I like about generic programming is focus on algorithms. It focuses on getting things done, and I really like that because there's a lot of fads in our field. Things that don't quite do a lot of work. They kind of, dance around doing work, and they kind of, pretend that work doesn't exist or whatever. I like this. I like that it wants to get job done, right? Focus on algorithms. It's great. Good abstraction power, as we know from the designs that were successful using generic programming. There's no indirection, so there's good speed. Awesome. However, I also figured there are quite a few disadvantages to it. I found generic programming to be overly rigid, very little adaptability. So you gotta define your interfaces in terms of these notions that the respective consumers require, and if you don't, you can't. Just doesn't work. It's very rigid, very frail. Only works for small and scarce vocabulary domains. How many primitives does a range have? We have 3 primitives, right? How many range type kinds are out there? There's 4 named kinds of ranges. And here it's kind of, we kind of start to, this emperor, I can see through that underwear. There's something wrong here. We don't have many. And generic programming is obsessed with naming everything. Everything's got to have a name. Everything's got to have a name. You got to name your iterator. This is a forward iterator. If it's not, I don't know what it is. I have no idea. The hell with it. Right? Nomenclature is central to generic programming. It's a huge thing for it. And, I don't like this because allocators are a huge vocabulary domain. And to wit, we have already betrayed the rules of generic programming. By canon generic programming, all kinds of ranges should have a name. And so we have input range, forward range, bidirectional range, and random access range. But we also have capabilities that are in a cross-product relationship with ranges. Has length. Can you have an input range with length? Apparently you can. You can say can take exactly of a stream. You can. There is such a thing. And it's useful. It works. It's good for us. So now we have, we're just not doing ways the generic programming canon. We're breaking it already. And I admit, I was afraid. I wrote most of this stuff, and I was like, whoa, this is kind of, is it gonna even work? Is it going to be of any success? Is going to be is going to hold water? Walter? It's going to hold water. So, oh, that's the worst pun ever. Okay.
We're laughing at you, not with you.
Right, it's at me, not with me. All right. So we have, we have all of the above with has-lang in tow. Boom. Well, we have this infinite thing, and here's sort of a limited cross product. So actually, you have to take care in exercising these names. Can you have a bidirectional that's infinite? Dave is going to say yes, and there may as well be. When Dave mentioned that yesterday, I was like, well, let me think of one, and I couldn't find one, and I'm sure someone is going to come to the microphones, and there is one. But it's sort of a strained concept, and maybe you don't want to support it. A bidirectional range you can pick from both sides, and yet is infinite. It has a really fat element in the middle of it, right, or something. All right, has slicing. Has slicing is interesting because you can't. Okay, there we go.
Bidirectional range where front and back are the minimum and maximum of an interval, and you can shrink it infinitely close and never get to
The limits of an interval, and you can shrink it, get infinitely. Oh yeah. So you need infinite precision math for that kind of thing. Yeah, excellent. All right, and soon there's going to be another guy coming to the microphones who's going to say pi contains everything in the universe, right? And I destroyed you. Okay, so we have has slicing, which is interesting because you got to think of it like, well, has slicing really applies only to random access ranges. Let's face it. But not to all, because you can have a hash table that doesn't have interval computation that's cheap. Right? It gives you access to any one element, because a hash table, but it doesn't give you access to a range of elements between this guy and that guy, because it's not sorted. So you can have such a thing as a random access range with or without slicing. Okay, so far so good. So it's not really a Cartesian product, it's an almost Cartesian product. You can have a random access range that is infinite, by the way. That's a given, right? That's obvious. Has mobile elements, can I move from front? I may have uncopyable elements, can I move from front? And this applies to everything. So, if we were to go with a canon, we'd have to define a bunch of names there. And, I didn't have room for everything because the font would have gotten too small, right? And this is LaTeX. He doesn't allow me arbitrarily a small font because that would be not stylish, and LaTeX would just explode and die and kill me in the process. So we have, we're breaking the canon of generic programming already as of today. And I was afraid to do so, to embark on that road. And, today I can say, and it was very good. Actually, I could even say it was very, very good, to quote a living classic, right? So it was very good. It worked. Everybody's happy. It's like not one peep, not one guy said, we got to put a name of those things or else. What the hell is going on here? Right? So it was good. So, well, this was a CD allocator, and, we have an allocator in the works, and actually, I went through a number of titles until I said, I gotta go big or go home. Allocators are really a pretext here. But, I tried to design a generic allocator, and I couldn't. It took me a year and a half to figure it out. And it's sort of the most trivial. And for some people, it's like, okay, let me. What's in an, for some it's a soul front, just plug in jmalloc and you're done. It's a great allocator, right? But actually I wanted to make one that's highly customizable, easy to experiment with, easy to improve, awesome. I wanted to have a good design. All right, so first thing I noticed was, well, there's a bunch of notions in memory allocation. It's just a bunch of stuff going on. We talk about alignment, we talk about dynamically aligned allocation, so I want to allocate, but it better be aligned at this particular part of 2. We have things like I want to round up the allocation, quantize the sizes so I don't put too much strain on the allocator. We have things like I want to expand this chunk of memory in place. And I may or may not be able to do that because there's allocators that structurally are unable, by design, they're unable to do that kind of stuff. We want to reallocate. Again, there are allocators that don't know how to reallocate. There are some that know, there are some that have no idea. We have contiguous versus non-contiguous allocators, meaning one can say, whatever you do, your allocated memory will be in this block of memory, right? Whatever you're up to, if you call allocate or whatever, the memory I'm going to give you is here. What's a nice consequence of that? You can real fast figure out whether a given block of memory is in that particular allocator. So that's a O of 1 operation is nice. Speaking of which, ownership. So this is a common thing. Yeah, I have a block of memory. Which allocator does it belong to so I can know where to, whom to address for either freeing this block, extending it, or whatever. So I have notions of ownership. We want to resolve an internal pointer. I give you a pointer randomly inside the buffer allocated previously, and where does where does the block start and end? So we want to resolve that internal pointer. And that's how our GC works, by the way. You need to have that primitive. Deallocation, of course, we want to deallocate. Surprisingly enough, there are allocators that don't know how to deallocate. We have per instance state versus monostate in allocators, meaning you create an allocator object, and it may actually have a size, right? It may have state within the instance. malloc is not like that, because all of the state in malloc is global thread shared, right? And and or thread local, but essentially it's like everybody calling malloc is going to hit the same data. There's no, I'm going to create one mallocator right here and kind of have a separate heap there. So there's also the state discussion here, and of course there's the thread local versus shared. Maybe it's on the stack, maybe it's wherever it is, etc. So look at this. This is not 3 primitives. This is not 4 ranges. So if you try to define concepts for all combinations of this, you just can't. You're going to give up. You know what? I'm going home, right? So high vocabulary. There's just plenty of stuff. So I really tried to design a generic allocator using the canon of generic programming. Didn't even get a t-shirt out of it. And then I kind of, what would be the next step you would do when you completely failed at doing something with what you have?
Something new.
Something new. So I did something new. What is the most famous quip from René Descartes? Cogito ergo sum. I think, therefore I am. So funny thing, the Portuguese-speaking guy said the English version, and the American guy said the... Okay, so, but do you know what he did before that? Aha. No, not math. I think that was after. Just before this. How did he reach this seemingly trivial conclusion? What did he do just, a step before that? Well, a step before that, there would be like, I doubt, therefore I think. Dobito ergo cogito. So he said, what am I doing here? I'm doubting everything, right? So Descartes, like, his claim to fame, he's doubted everything. Like, he would say the emperor has no clothes, even if the emperor was fully clothed, okay? Even with a dressed up emperor, he would say, you know what, I'm not sure there. So Descartes, the first thing he did was to free his mind of everything. He freed his mind of all of the preconceived notions he had. I said, what's left? Well, what's left is I'm doubting everything. And, well, it looks like I'm thinking. And I'm thinking, therefore it must be existing because there must be something doing the thinking. Therefore, there's an existence at stake here. I'm not kidding. This is what he did. And then it goes more weird after that, but this is like a huge notion. You know, and there are a lot of things that exist but don't think. But for him, it was, well, these are like what my senses tell me exists. This table, you know, whatever, string theory. It wasn't yet invented. But anyhow, so, you know, there's a lot of stuff around him, but he couldn't because everything was intermediate through his senses, which could be as well failing him, right? So he said, let me empty my mind of everything and figure out what's left. All right, if you free your mind of everything you know, and you think, I want, an allocator would be good for my life right now, what is the one primitive you want? Give me memory. Allocate. Allocators must have one method. Allocate. That's easy, simple, trivial. Even they still got it. That was a joke. Like they still allocators like universally reviled, right? So even they got this one primitive right. So the only thing we want is to allocate memory. And here we enter what I'm proposing to you today, design by introspection. It's you build designs from components by looking what they can do. Let's see. Going with the allocators, let's think of the simplest design that could possibly work. Everything is optional in the allocator design. All of that large vocabulary stuff, optional. You may or may not have it. But we need one thing, allocate. Give me a number, I'll give you a buffer. This is allocate. Soon thereafter, I figured there is this one piece of reality that pervades allocation, alignment. Every allocator has got to define what alignment they offer. Usually it's like word aligned or kind of 16 bytes or whatever. So there's something, for every allocator there's going to be an alignment. So actually this came up so often I decided to make it a primitive. This is Descartes, this is experience, right? It's honest and it's fair. I think it's a fair thing, right? So I thought, let me write an allocator that only has these two things, right? Everything is optional and is probed introspectively in generic code. And the simplest primitive that I'll use here throughout these slides and in most of my design is going to be a simple utility in the traits, has member. If a type called A has a member called expand, it's going to return true, otherwise it's going to return false at compile time. Boom. So far so good, right? Nothing up my sleeves. So what we want to, where we want to get from here is to get to allocators that define and adapt their own capabilities to their hosts, their parameters that are also allocators in very little code. I'm going to give a few examples of that. The simplest allocator that people want to define, and actually it's pretty useful as a basis for a lot of other allocation strategies, is the region. Push the pointer. You take a region is like a hunk of memory, you pre-allocate it, 1 megabyte, whatever, you want 4 kilobytes, 64 kilobytes, whatever works for you. Take a hunk of memory, put a pointer at the beginning. Whenever somebody tries to allocate, you give them this portion, bump the pointer, and then you have this left. And then there's another allocation, push the pointer, and then another one, and so on. This is the absolutely simplest design of allocator that could ever be made to work. It has alignment 1, because I can ask for 1 byte, and it's going to push the pointer by 1 byte, right? So then the pointer, that tracer, P in our example, could actually span all the addresses between begin and end. So initialize it with a buffer, etc. Do I need to really explain this? There will be one thing, this test here, that's important. If the buffer is sort of done and I don't have room for the new allocation, I'm returning null, which means I'm done. I return the null pointer to the null buffer to signify that I'm done here. There's no more to allocate. And this is actually important. It's not throwing an exception. It's not a irregular state. It's okay to fail, right? And I'm returning the result, P plus equals N. This is like really fast and nice and everything. Region allocators are super fast, which is awesome if you can use them. So this is the simplest allocator that can be made to work. Notice, it can offer no other primitives. Has alignment, has allocate, does not have deallocate. It has no idea how to deallocate. Doesn't have structure to go back and kind of deallocate blocks that have been allocated before, etc. All right, so there are a few immediate improvements that can be done to this guy. Well, let's face it, alignment of 1 is like you almost never want it, except if you're doing strings. Most of the time you want kind of word align and kind of align to the worst alignment of any structure you have in your program. That kind of stuff. So there's a platform alignment that you want to support. How do you do that? How do you fix that in our code, Steve? You pad the result. Actually, there's a simpler approach. You pad the size before allocating. So you start with an align buffer. So you kind of verify here that it's aligned properly. And then you say, whenever you allocate, first step you do, you round this up to a multiple of your alignment. And it turns out this works. And it's cheap. It's nice, right? You could run the pointer after allocation, but it's just as cheap, but it takes 2 casts, and you gotta manipulate the pointer like it were an integer, so it's not that elegant. So you just pad the size, right? Nice. So, well, there are a few more things. You can embed the buffer straight into the allocator, which makes it suitable for stack allocation. So you can actually put, instead of having a parameter here, you can actually say, well, I'm gonna allocate right straight in here a void of whatever fixed size I want, my buffer. And that's going to be an in situ region, if you wish, right? Nice. Maybe we want to release the buffer in destructor. Maybe we want to define a destructor that whoever gave me this buffer, I give it back to them. So maybe I malloc a megabyte of memory. I initialize a region with it, and when the region is done, it's going to free the thing. So this is also an option that we can think of. And there will be some new primitives that are interesting. There's deallocate all. How do you implement deallocate everything on this design? Deallocate everything.
Is that the point of view?
Yeah, P equals B, right? Boom, we're done. O of 1. So deallocate all. Notice that with a lot of other allocators, that's an O of N operation. So it's kind of interesting that we can define this in so brief code. All right, so these are sort of trivial and are kind of strictly related to allocation, but not to sort of the introspection-based design notion that I'm talking about. So let's move forward to the simplest composite allocator that could possibly work. I figure there are a number of idioms in the literature, and people talk about such. And the simplest is a fallback allocator. It takes a primary allocator and a fallback allocator. It goes like this. Well, first I'm going to try this guy, the primary. That guy works, I'm done. If that guy doesn't work, returns null. Interesting. Then I'm going to use the fallback allocator. So I'm going to have 2 members. Note that I'm even making them public because, I have no shame in what I'm doing here. Right? And, well, there's a piece of interesting code here. Well, the alignment, if you sit down and think about it, is the minimum of the 2. It's a kind of worst alignment, right? So already we have a notion to, so this kind of a mini reason of pride because, that looks like a good design because I could define the alignment of this guy in terms of the alignment of those 2 other guys, which is nice. And then I define allocate. I'm trying the first allocator. If I didn't make it, then I'm going to allocate from the fallback, and then I'm going to return the buffer. Notice that here I'm comparing the length against n, and I'm not comparing the pointer against null. Why? Come again?
Null pointer might be valid on some
Null pointer might not be valid. It's a singular pointer. Yes?
And people allocate, they expect to get a contiguous amount of space, and if you didn't get it from the first one, you'll have to ask it from the other one.
When people ask, they're asking for contiguous, memory is going to be contiguous from either allocate. I'm not returning a combination of the 2. So that's not, you're not there yet.
But this
Well-
is why you're asking for n and not null. If you didn't get enough, you just want the whole.
There's a subtler reason. There is a subtler reason, yes.
Misaligned allocations. Your alignment aren't the same.
No, misaligned allocations are not. Clearly, we could adjust this to do the alignment better. You're right. This routine doesn't do good with allocation. But there's another subtler reason for this. Steve. Who said 0? All right. If you ask for 0 bytes, if you ask for 0 bytes, an allocator, essentially everything is a success. Right? You can return null, you can return a pointer. I decided to make all allocators return null if you ask for 0 bytes. It simplifies a lot. But you could go either way. Essentially what I'm saying here, because I'm checking this way, I don't need to check for n equals 0 in the beginning. Right? Yes?
Well, if the primary allocator gives you more bytes than you asked for because it's added.
It might give you more bytes than you asked for. So the question was, what if one allocator gives you more than what you asked for? It does, but it's always going to dial it down to n bytes. The contract here is it either returns a buffer of length n or null. So this is, again, a thing that simplified a lot of further designs. OK, so this is the simplest that could work. So now, again, we have allocate and alignment, and we're done. But sometimes we want to deallocate things. And here's where things get interesting. This is where we're starting right now, past half time. OK, so we want to deallocate, for example. Oops, oh, sorry. And suddenly we have a design, because we can front a region with an allocator that just implements in terms of malloc, and we have an allocator working. And we can actually sit down and test it right now. It tries the stack first, and then it tries malloc, and it just works. But because we use malloc here, malloc is a very simple allocator. It has no state, has allocate forwards to malloc, you're done. So this is not much to talk about. But the first thing we're thinking about here is like, well, if you allocate with malloc, you get a free with free. So we want to deallocate at some point. So, well, let's kind of go, again, the simplest deallocation that could possibly work. We want to deallocate that takes a buffer, returns void. And here's what the method looks like for fallback allocator. So first of all, if you think of it, you need to add one more primitive, which is owns. Because when I receive a buffer back, I need to figure, was it from the primary guy or the fallback guy? Where did it come from? So I know how to pass to it appropriately. So notice I'm just following the white rabbit here. I'm not doing anything interesting, original. I'm not trying hard. I'm not trying at all. I'm like, well, we need the allocation. If we need the allocation, we need owns. And that's how good design is born. You go with the minimum you need, and then you grow as it happens organically. So we need owns. We need a new primitive, bool owns, that returns true if this block is owned by this allocator. All right. With that in hand, we're going to use this constraint here. Well, static if P has the member owns, well, it's got to have that. The primary allocator must have owns. And at least one of these two guys has the allocate. So there's a little Boolean algebra here going on. Right? So what I need is P to have owns and at least one to have the allocate, because otherwise there's nothing to do. I can't deallocate anything. Right? So this thing is my gating factor here, is my condition that makes the allocate even definable. Right? And here we enter the definition. And, well, if the primary allocator owns the buffer, then I'm going to look for its deallocate member, because it may or may not be there. I'm going to look for deallocate with static if. And if it's there, I'm going to deallocate from the primary. Otherwise, I'm going to look whether the fallback has the deallocate method, and if there, I'm going to call it. Yes?
if it doesn't have owns and you want to combine it with mallocator, you're going to leak memory, no?
If it doesn't have owns and you want to combine it with mallocator, it cannot define the allocate. That is correct. All right. I want you to contemplate two things. Oh, yes, Robert. Why don't you move to this other one? Thanks, Chuck.
So I assume P and primary is the same thing, right?
Primary, where is primary? Oh, here, yeah, this is a typo.
Yeah.
So I had to
And
shorten all names.
Like
so
another
thank
question, the return on F deallocate is useless, right?
You.
Yeah, the return in front. I mean, for primary, you just...
Yeah, that's fine.
Okay.
This is just going to work by double mistake, but this got to be P, right? So essentially, my code online is a P that it uses primary and fallback for nice names, but the slides will go like way there. So I shortened the names, and apparently I forgot to shorten everything. Leo.
Why would you use OR and not AND for has member deallocate?
Because this allows me to create the region that fronts the mallocator. Region doesn't have deallocate, but it does have owns. How do you implement owns for region? You check a pointer against the bounds, you're done. It's a very fast operation. So region has owns and doesn't have deallocate. Do you want to put a name on that? Because by the canon generic programming, I would have to give a name to everything. Allocator with owns but no deallocate. Allocate with allocate and deallocate, but now reallocate. Allocator with allocate and deallocate, but no expansion and reallocate. It's crazy. You can't. It's just impossible in a large vocabulary domain to put a name on everything. Not all designs can have a name. It's like lambda of designs, right? You gotta go with lambdas. So, well, another interesting detail here is that F fallback does not have to define owns. Only the primary, only the guy in the front needs to define owns, and the guy in the back does not need to. And this is a sort of a fact. It's there. It's not something that I proved. It's not something original that I say. It's there. It's happening, right? The only thing I can say about that particular piece of design is that happened, right? Okay. But it's very interesting because, for example, the mallocator does not define owns. So it makes sense to front a mallocator with a region, but not to front mallocator on top of anything else. So it's kind of, there's an interesting harmony to this design. And it stems in two things. One, I made everything optional, and then I figure out what's the minimum I need to implement deallocate. And the second is I use some Boolean algebra in here, which would be very difficult to express with types. It would be like, it would be killer. Other languages do that. They do everything with types, and they have algebra on types. We use like plain old Boolean algebra, and it just works for us, and it's fantastic. And actually, these conditions turn really interesting because you look at them and you understand things, because you understand what you need to do things. All right, so only P must define owns. Well, we talked about that. So let's take a look at all the optional methods we have, and I'm going to swap screens here. I'm going to talk just a bit about each. So we have alignment, which we talked about. We have a primitive that's a good allocation size. Given a number, give me how much you're going to allocate anyway. That's my good allocation size. If I give you a 3, maybe you're going to give me back 64. If I give you 4,000, maybe you're going to give me 4,096. So that's for the client code to optimize internal fragmentation. All of these had a need for them. That's what I'm saying. Allocate, obviously. Aligned allocate allocates a specific alignment. Allocate everything, which is great for region. I'm allocating all the memory in this region and manage it a different way. It was useful. Expand, give me a reference to a buffer, give me a delta, expand it by this much. Reallocate, give me a reference to a buffer, give me a new size, I'm going to reallocate this. It may move the memory. Expand can't, right? Align, reallocate. The memory was aligned. I want it to stay aligned. Why no aligned, expand? Align, expand. Why not? You don't need it because I was checking if you're paying attention here. All right. Owns, we talked about it. Resolve internal pointer, we talked a bit about it. I give you a pointer, give me the buffer it sits in. Sometimes it's needed. Deallocate, deallocate all, which is goes in pair with allocate all. Empty, does this allocator manage any memory? If not, it's empty. Like at the very beginning, it's empty. Zeros allocations, I'm gonna remove it, I don't like it. For monostate allocators, it just, say allocator.it, and it's giving you the one and only instance of the allocator. This is how we solve the matter of monostate versus per instance state. And here there are some routines I'm not going to release now. All right. So all of these, they're like, 20 methods in there. I didn't count. There's a bunch. And you can't define a notion, a concept for every combination thereof. You just can't, right? So that's why I'm going for designing through introspection, looking at what things can do and making decisions appropriately instead of going with one of the non-design techniques. By the way, for this fallback allocator, it's easy to propagate owns. If it so happens that both allocator implement owns, again, there's a conjunction here. I'm going to, I own this, as the fallback allocator owns this guy if either of my constituents own it, right? Notice that we have like an AND here, a NOR here, so again, some Boolean algebra, which is nice and simple and easy to understand, and I like it. All right, so owns is part of fallback allocator if both these guys define owns. Well, how about reallocating memory? So we saw this primitive reallocate, and it takes a reference to a buffer and a new size, and do whatever the hell it takes to reallocate this buffer to this new size. Boom, right? And here's kind of, this may as well be one of the nicest functions I've ever written. So it fits on 3 slides, but it does a lot. Well, reallocate by definition, if you ask for 0 bytes, it's got to deallocate. So, okay, well, if the new size is 0, we're going to say, well, can I deallocate? And if so, deallocate, return true. Notice this line here. This is reflection. This is like, do I doubt? Do I think? Do I cogitate? Do I exist? This is Descartes in all its glory. So, because essentially deallocate is defined elsewhere with other conditions on it. If, if that guy defines deallocate or the other guy defines deallocate. So there is a condition that gates the definition of deallocate. I may or may not be able to deallocate, and I don't want to repeat that condition here. All I want to ask, can I do that? If you can, you're going to deallocate. Otherwise, you do nothing. I'm successful. I'm fine. What?
Shouldn't you instead check for actual signature necessary for delegation?
Shouldn't you check for the actual signature? Yes, I didn't want to bloat the code and the slides. Do you define deallocate that takes a void buffer and returns void? I decided to go away without doing that because the simple reason being, if I claim something is an allocator and it defines something called deallocate, it better be with the canon signature. So I simplify my life. Truth be told, it should be checked for exact signature. All right, so I'm done here. Well, if B is null, then reallocating from the null pointer by definition needs to allocate. So I'm going to take care of this. Actually, I took care of new size 0, so this is correct. All right. So this is sort of trivia. So the first page in this implementation is kind of trivial stuff. And then I'm going to, while still in the function, I'm going to define a template function. I'm inside the template method that's guarded by a condition, and I sit down and define a template function, which is really neat to do. I mean, it's one of those, like, you write the code and you're asking yourself, am I breaking any law of physics here? any law of nature is like at stake here that I shouldn't allow me to do that. So I was very happy to write this code. I'm telling you, I almost was annoyed by coming to this conference because I wanted to sit down and write more of this. I'm not kidding. And the only thing that makes me happy is that I can share it with you now. So cross-allocator move. Well, I need to move from F to T from 2. So I'm moving from one allocator to another allocator. And I'm going to say, well, allocate the new size in the 2 allocator. I'm going to explain exactly why I need this. Well, allocate some memory here. If not, I'm not going to work. Then I'm going to, what's this? Moves the chunk of memory, whether larger or smaller, moves whatever memory is being used. This is moving the memory. And this is going to deallocate. And then we're done. So again, I am inside this method, bool reallocate, ... follow the rabbit, ... This is a function definition inside of it, which is templated. And why do I need that? Because here's sort of the pride, the magician's pride. Here's what makes this really cool. Well, if there's no buffer or the primary allocator owns the buffer, then I need to let's try to reallocate within that primary allocator, right? So if that guy works, I'm done. Otherwise, I want to move the memory from primary into the fallback allocator. And that's how my reallocation succeeds. I'm seeing a few like kind of blank stares here, so I'm going to kind of pop up a bit. So what we're looking at, we have the fallback allocator. It holds 2 allocators. You give me a hunk of memory and say, reallocate this gentleman. Okay? So what I can try to do is if it's in the primary, try to reallocate with the primary guy. If it's in the fallback, try to reallocate with the fallback guy. But there's also a third possibility. Well, it may be in the primary, but there's room in the fallback for the new guy. So I can move the memory from the primary to the fallback. And vice versa, it may as well be in the fallback and I could find room for it in the primary. So all of this stuff is necessary, is good. You want to succeed at doing that. So this is what that code does. It defines that generic function because it could be called with swap arguments, either one way or the other. Okay, I'm starting to see knots here. So that's what I'm doing here. Well, is it in the primary? Can I reallocate within the primary? I'm good. Otherwise, I'm going to cross-allocator move from primary to fallback. Otherwise, can I reallocate within the fallback? If so, I'm done. Otherwise, I'm going to move from fallback to primary. I want you to picture this. How many lines of code would it take to do this in any language? How many lines of code would you need to do this? There's no repetition here. So this guy is instantiated twice. One with this, one with that. It's the same code, right? And it's defined inside a function, which means there's no unnecessary instantiations. So this is awesome. All right. Actually, to tell you the truth, there's a global reallocate all the way at the top level. Because if you have an allocator, you have a buffer, and you have a size, you know how to reallocate. Here's how. Well, can it expand? If the first thing I'm going to try in reallocation is to try expansion because it's the cheapest. Can this guy expand? If he can expand, I'm going to try to expand. Otherwise, well, let me do the allocation, check for success, move the memory, deallocate the whole buffer. Again, I want you to contemplate how many lines of code does it take you to write this function in any language? How much thinking it takes? Because this would be a paper. This would be an article. I did this in this language, and it took me only this long. It's parameterized on this guy, and so it already has like 4 combinations going. All right. The last I'm going to talk about, because we don't have much time, is the segregator. A very common pattern. I have a threshold, everything small goes to small, everything large goes to large. There are allocators specialized in allocating only small buffers, small objects. So if something is below, less than or equal a fixed number, then I'm going to use this guy. Otherwise, I'm going to use that guy. Question, do you need owns? Do you need owns? Because the structure is similar to fallback. It also has two allocators. Do I need owns? No, because I have the size. I know where it goes. When I deallocate, I have the size. I compare the size against the threshold. I know where it comes from. Right? So I don't need owns. Another kind of factoid there. Again, the alignment is the worst of both of the two. And then allocate is trivial. If it's less than or equal to threshold, I'm going to use the small. Otherwise, I'm going to use the large. And I'm sure you can fill in a lot of blanks here. Now, I'm going to explain one more method that belongs to this guy, which is, again, some sort of an interesting method, expand. So again, for this segregator. So OK, here goes. So we have, if small allocators has the member expand, it knows how to expand. And the large guy knows how to expand. So at least one of them knows how to expand. Then I'm going to commit to defining expand. And the way I work is, well, let's see. Do I go from small to small? Old and new allocations handled by small. Oh, and here I have a few typos here because it's kind of underscore small, right? Apologies about that. I'm sure you can follow, right? So if the small guy knows how to expand, then I'm going to call expand. Otherwise, I'm just going to return false. I couldn't do it. And if the length is beyond the threshold, I know that old and new allocations are going to be handled by large. So I'm going to go with, let me see if the large guy has expand. And again, I'm going to return true if successful or false otherwise. Notice that if it's not defined, I just return false, right? But I commit to at least trying one because of that or at the top, right? So, here we would have a case in which just we can't do anything. That would be, actually, I think, you don't need this. So everything returns. All right, so with these examples, I hope I explained a few tenets of design by introspection. And here's how I see it. You compose larger designs from small pieces. You decompose as a matter of course. This is sort of a classic design kind of pattern that everybody does, wants to compose larger designs for smaller pieces. But the interesting thing here is we want to distinguish the required from optional methods. This is new. I didn't know that was physically possible. I didn't think it was appropriate. I thought maybe that's a bad word, right? Maybe that's not. It shouldn't be said in polite company. So we want to distinguish what's required from what's optional. In my design, I made everything optional except for like 2 primitives. No need to name all combination. And for that, generic programming is fail. And concepts are a big fail. Because at least generic programming did something. It has results. Concepts don't have results. So concepts are, we tried, yeah. So this is kind of the funny thing. Concepts like the date your mom loves, right? So, it's like, oh, marry her. She's awesome. She has a college education and a symmetric face. And if I spend one more dinner with her, I'm going to kill myself. And then I'm going to kill her, right? I mean, concepts are like what everybody wished worked. Right? Everybody wanted them to work. I wanted them to work. I wanted to love them. And I had to go Cartesian and say, you know what? This is crap. This doesn't work. It's obsessed with giving a name to everything. The main problem with concepts is they gotta put a goddamn name on everything. There's a shit on the road. It's gotta have a name. Call it James. I don't know. Give it a name. I hope there's no James in the room. All right. So concepts are fail, and I was very surprised to notice that. I really wanted everything else to work, and when nothing worked, I had to kind of figure out what to do. To do design by introspection, you assemble things by looking at what they can do. And this is what allocators do. They have these small components and then build from there, build up and up and up you go, which is pretty amazing. And I got to like a number of components that are just incredibly generic and they do a lot of things. Use Boolean logic and static if. So Boolean logic was like a huge win for constraints in parameterized types for us. And static if is an absolute lifesaver. There's no way I could imagine myself doing all of this without a facility such as static if, because otherwise, you know, it's very fluent to have static if. You just write something else, oh, can this guy do that? Static if, oh, then do that. Okay, otherwise. Without it, I would have to, stop, full stop right here. I got to write a new template, right? So they constrain both types and function signatures, and also like, you know, static if is used inside functions. So yay to that. All right, take a look. So I have the links here to the documentation and the code, code and documentation that is. And I couldn't not share this. We're running just a bit over, we're just running a couple of minutes over time, but I gotta give just one more slide. There's something that I run into that I called Ouroboros style design, which I just loved. And I think you're gonna love it too. Here's the thing. I wanted to define an array of allocators. It's not a big deal, right? Here's the goal. I want to define a global array of generic allocators. For example, I could have an array of regions or an array of heap blocks or whatever. There's a number of things that I define there. And it's natural to have an array, and kind of as you need more memory, it kind of grows. As you release memory, it kind of shrinks. And it's kind of a simple structure. And to keep some simple metadata for each allocator. So it's an array, a dynamic array of allocators. And the question is, where do you store the array itself? I'm not kidding. Where do you put it? The mother of all allocators at the top. That's an option. So you could say, you know what, I'm going to use the GC allocator, or the mallocator for that particular metadata for that array. It grows, it shrinks, I reallocate, no problem. And the data of the allocators is there, right? What if I don't want to link with malloc, or I don't want to link with the GC? Because as people say, I don't want to link with the GC, right? What if I don't accept that? Well, there's plenty of memory where that came from, because I have an array of allocators. What do allocators know how to do? Allocate. So, you know, kind of, Sarah thought, is this even possible? It's one of those instances. Is my computer gonna burst in flames if I write this? Okay, am I breaking a law of nature? Am I, you know, is my work gonna be rejected by France because it's not, it's a perpetual motion thing? You know? You know, France didn't recognize relativity theory until like the 30s. No, the 60s, 50s. They're like very late in the kind of.
They wanted to make sure.
They wanted to make sure. They had to be real sure that relativity works, and they kind of just didn't. You know, that doesn't work. All right. So you know, similarly, well, here's what I did. I create an allocator on the stack. It's within my rights as a citizen to create an object on the stack, right? It's in my Bill of Rights. Okay? It's the Fifth Amendment, right? They call it. All right, so I create an allocator on the stack, and then I can use it to call allocate and allocate memory as needed. So I can use it to allocate me some memory, please. There you go, sir. And I got some memory. And then what did I do with that memory? Well, I moved the allocator state from the stack into memory allocated by itself, thus completing the Ouroboros design. Ouroboros is that snake that eats its own tail, right? So I moved the memory from the stack of the allocator within the memory that the allocator just gave me.
You just solved the halting problem.
I just solved the halting problem and perpetual motion and a couple of others. So, just don't what?
Free it.
You can, yeah, just don't free it. Actually, freeing is interesting because you do the reverse. You gotta vomit your tail, right, if you wish. So, all right, so create this guy, you move it to that memory, and keep a pointer to the metadata and the meta allocator, and that works because the pointer is constant size. I don't need to grow anything. So I have just a pointer, and I'm done. So then whenever I reallocate it, I do the same trick all over again. And it's kind of funny because it's one of those rare instances like where you code and say, is this even reasonable to ask for? Is this okay to wish, right? Or am I high, right? That kind of stuff. So this really nicely solved the problem. And again, when you deallocate, it's sensitive, it's interesting. So you gotta do sort of the opposite. And one more thing was, what was it? When you allocate. I forgot. But this is like the gist of it. It really works. Oh yeah, I remember. When you move, you can't use std move. You can't use std algorithm move because it asserts. It detects something fishy is going on. It's like you're moving this guy inside itself. You can't do that. Jesus, you can't do that. This was in the error message. Jesus, you can't do that. It was right. So the thing asserts left, right, and center. It just doesn't allow you to do it. So I had to use memmove. Memmove was like, what the hell? Do it. Do it. All right. So problem solved beautifully. Take a look at allocator list. That's the implementation. Allocator list. And you're going to see there's an array there. It's a list because it's a most recently used list maintained in there. That's the metadata. So it's amazing this even worked. So I'm very pleased. To summarize, generic programming didn't work for me. Insufficient for flexible design. I'm proposing design by introspection. Use it. Give components required and optional APIs. Use introspection to assemble larger designs from small components in a very flexible way. For my money, here's the thing. Here's what I think. I think if you have these, static introspection, compile time function evaluation, Boolean constraints, and static if, win. Thanks very much.
I just realized that you described what I did with my serialization library a year or two ago, so I'm going to claim early adopter.
Awesome.
And secondly, how do you debug this when you want an allocator to have the allocate and then it doesn't work?
When you want to allocate, that it can't happen if it's a region that's on the stack. It can't allocate its own size.
I mean, because of the introspection, sometimes that might fail because one of the static ifs will fail because you made a bug when you're designing your thing. So you want it to deallocate, but it doesn't because some static if somewhere fails. How do you debug that?
I'm not sure. Oh, you want to deallocate, but it's not defined, right? You want to deallocate, but you build the allocator in such a way that the allocation is not possible?
Yes.
You look at the design and see where it failed. I'm
just saying that I've had similar problems with this with my early adopter status, so.
Right. It may be interesting to list the capabilities of an allocator. That should be easy with Pragma message to say, here's what this allocator can do, and here's what this allocator can't do for the following reasons. It's a nice point because all that Boolean algebra can kind of confuse.
Well, a really stupid, simple example is if I misspelled the allocate.
If you misspell the, but that can happen in any design.
I know, but debugging that is hard.
Okay, Adam.
Just another solution to that, if you do static if has method, and then inside that you do static if matches the correct signature, then you use it, else you issue a custom error message.
Okay. So if there's a mismatch in the signature, you can actually detect them.
Catch a misspelling, but we can catch a signature.
Right.
I think it's worth doing that in Phobos. I don't know about anywhere else though. A lot of code.
Thanks.
But just along those lines, what Dicebot was pointing out with just checking whether it has deallocates is nothing but whether there's the correct signature. It should be trivial unless to do what we're doing with ranges right now with has length and other things.
Yes.
Just make sure it's correct.
Right.
We might want to have the additional has member to make sure it's not using universal function call syntax, but it should be trivial enough to just wrap those to do the full check.
Yes, you could actually for each of these guys. Let me find. For each of these guys, you can say has expand and has length and has empty and has deallocate, etc. Yes. That's an obvious course of improvement there. All right, we're way over time here, so let's talk some more during the day, and thank you very much.